Ah, a guest. Well, welcome. My name is John Carlini, and this is my den of knowledge, home to only the most cerebral and informative works of writing. Okay, you got me. I'm no genius intellectual or expert in any particular field. I'm just a run-of-the-mill physics major here at Schoolcraft College, like you. But as any physics major should know, labs are one of the most important parts of understanding the material. However, I've noticed that I've occasionally had some trouble keeping track of the instructions in class. Sometimes I just fall behind the professor due to technical issues, or other times the paper instructions can be less than clear. That's why, with the help of Professor Chris Wood, I've made this video to help you understand the content of the lab completely beforehand. This can be watched in class or beforehand by sending the students a link. Either way, my hope is that this project helps make the lab easier for everyone without compromising its educational value. But that's enough rambling from me. You don't care about that. Let's get to the science! As that Technicolor intro and video title probably already told you, we're going to be working with heat engines today. A heat engine is an ingenious little mechanism that allows one to create work out of a simple difference in heat. Specifically, we are going to make a piston rise through the difference in heat between boiling and ice water. Professors, if you are showing this in class and have somehow forgotten to prepare the ice required for this lab until now, then this is your best opportunity to grab some. Go to the gas station or something. You'll probably be back before this video is over. Maybe. Anyway, back to the video. Before we do anything else, we'll need to do the actual setup. For this lab, each student, or group of students, will need the following. 2 large plastic pots filled with water, an A-shaped base, a metal rod, a mass hanger, a spool of string, a box of weights, a metal canister, a rubber stopper, 2 plastic pipes, an RMS pulley, a low pressure sensor, a rotary motion sensor, and finally 2 temperature sensors. Once you complete that fun little scavenger hunt around the lab, the time has come to actually put everything together. Begin by heating up one of the pots on a supplied coffee heater. It'll easily be boiling by the time you need it. You can leave the other pot empty for now. Hopefully the professor will be back with that ice by the time you need to fill it up. Next, you need to attach that rod into the clamp of the A-base. In turn, you gotta clamp that piston to the rod. Continuing on this train of thought, we gotta attach the rotary motion sensor to the top of the rod directly above the piston. Make sure it spins freely. Give it a little flick. Cut a line of string just long enough to triple knot one end of the piston, wrap around the motion sensor, and then triple knot the other end of the mass hanger. Just remember that string is cheap, but time is priceless. So just get a little bit more than you think you'll need, and if that's too long, you can cut it shorter. Next, you need to plug that rubber stopper into the metal canister. Additionally, you need to find the canister's volume to see how much air is inside. Obviously, you ignore the space displaced by the rubber stopper. So measure the dimensions of the canister, taking all that into account, and use some basic geometry to figure out the volume. Channel your inner plumber, because we're playing with pipes now, baby. Connect the canister rubber stopper combo, the low pressure sensor, and the piston all together with the plastic pipes. Connect all your sensors to the Pasco Universal Interpreter next to your computer. And while you're at your computer, make sure to open up Capstone if you haven't already. Make sure to set up all your sensors in the hardware setup menu before creating a new graph. Set the common sensor rate to 100 Hz. While you're in Capstone, feel free to set up the RMS as to the large pulley groove section, as well as setting the resolution to 1440 counts per revolution. Make sure the piston rod set bolt is loose so the piston can move freely up and down. However, you don't want it to be too free. Make sure the maximum displacement is 7.5 centimeters. Go back to the computer and set every sensor to scientific notation within 6 figures. Make sure the pulley string is properly aligned when viewed edge on. That could potentially mess with your data. And now, hopefully, barring some horrific accidents, your teacher should be back by now with that ice. So make sure to fill up your other tub with half ice and half molten ice. Water. That's a silly way of saying water if you didn't. Whatever. Make sure to stir it so it stays a consistent temperature. You don't want any convection to start happening. Attach 45 grams to the mass hanger as a good old-fashioned counterweight. Cross your I's and dot your T's by making sure all your units are right. Meters for distance, Kelvin for temperature, pascals for pressure, yada yada. And finally, you should double check for air leakage. The piston should rise slowly after pressure is applied to it, unless there is some sort of air leakage. Double check on this one, it could really mess with your data. Whew, now that grocery list is over, we can finally get to the fun part. First, I give the canister a little ice bath for a good 30 seconds. That way, we can be sure the system is filled with exclusively cold and dense air. The canister should be submerged almost to the rubber stopper, but not quite. Next, I depressurize the tube, set the piston to 20 millimeters with a 200-gram load weight on the platform before reconnecting the pipe. All of this has to be done fairly quickly. Now is when you start recording. I'll show side-by-side footage of myself performing the lab and the resulting capstone graph of pressure by volume. I'll make sure to stop when needed to explain the minutiae of what I'm doing. I now swiftly move the canister over to the hot water pot. As you can see on the graph, there's a spike in pressure that soon plateaus as the excess energy is converted into work which raises both the platform and the load it's carrying. Or at least you would be able to see it if my freakishly hairy arms weren't in the way. You'll have to trust me on that, it's definitely rising. Once the platform is at its peak, it's time to remove the weight before switching the canister back over to cold water. The cycle is now complete, and we have successfully done work with some gas station ice and an old coffee heater. So that's that. Follow each step of this video carefully, and you'll have a fully functional, if not slightly inefficient, heat engine. With some engineering know-how and clever thinking, this same fundamental system can be used to make the combustion engines just like those that are used to power cars, fly jets across the world, and irreversibly destroy our environment to all future generations. I'm gonna have a quick ponder session about that. Goodbye.